This is week 2. So on the midterm, there's, I believe, 6 weeks. So we only have 4 more. This is the second one. So this is for week 2, both lectures. Today we're going to be going over a couple things. One is going to be exponential distribution, which is the same as any other distribution, just different way to calculate it, I guess. We are going on discrete. So discrete variables for distributions. If you guys remember from last lecture, discrete are numbers that are 0, 1, 2, 3. They're not decimals. And we're going to be going over standard distribution. So for exponential distribution is, if you guys remember what exponential functions are, they're just, I'll share. Hold on. Ooh. Okay. So if you guys remember your exponential functions, they're just functions that, exponentially grow. So you have, this is, let's say, x squared, and then we have, I don't know what's going on with my mouse, x to the 4, which becomes even more exponential. And as you can see, the more this grows, the more exponential your function becomes. Okay? So for your exponential distribution, it's basically the same thing, except instead of it going upwards, it goes down. Okay, and that's what this negative here kind of represent. So exponential distribution with parameter lambda more than 0. So what is lambda? Lambda basically says how fast the exponential distribution goes down. So the bigger the number is, the more steep it gets. The smaller the number, the flatter it becomes. Okay, so that's basically what lambda represents. It has to be more than 0. Okay, because if it is 0, if you turn this 0, e to the 0 would give you 1, and then 1 times whatever lambda is. So and you can have negative, because then that makes it exponential, which switches the whole function. You don't need to know about that, just, lambda just tells you how steep it gets. If the density function for x, this is the function. But one thing about exponential functions, distributions in general, we never really use the equation as it is. Like, we have nothing to do with it. The whole point is we want the probability, which is the area under the curve. And if you want the area under the curve, you integrate. And so for this one, every exponential distribution, it uses this function, and then once you integrate it, you'll get e to the negative lambda c for some constant c and for some constant lambda. Well, actually your c is not constant. Your c would be x, but your lambda is constant. Now, what does this function give you? So let's say we have, this is our exponential distribution. Remember this one thing, and for exponential distribution, this is really all you got to worry about, is that your function, this one, after you integrate, so if you take this and you integrate it, this is what you'll get. And this one, whatever you plug in, so your lambda that will be given in a question, okay? So let's say your lambda is 0.2. Your c, when you're integrating, when you plug in c here, whatever c is, so let's say our c here is 10. If I plug in 10, it will give me my area under the curve to the right of whatever value I put in here. That's all you need to know for exponential distributions, okay? Is that whatever you plug in your c, or if you want to name it x, whatever you plug in there, it will give you to the right of that. So let's say I don't want to the right, I want the area under the curve to the left. Now you have 2 ways to do it. Is it 2 ways? I guess there's one, the easier way to do it is that, let's say I want the area to the left of 10. We know the area under the curve of any distribution, right? The integral from b to a of any distribution, is 1. So everything under the curve is supposed to equal 1. So if I want everything to the left, and I know this function gives me everything to the right of whatever number I plug in, I can easily just plug in 10, which will give me everything to the right. I know the whole thing is 1, so if I do 1 minus everything to the right, which is going to be my function, this will give me everything to the left of 10. So that's all you need to know for exponential distribution, is that if it says exponential distribution and it doesn't give you a different function, all you need to know is this is the one you'll use. Or if they don't give you this one, this is the one you'll use and you'll integrate. But I remember the prof saying you don't need to worry about that. This will be given. So Don't take my word for it. So just make sure with the formula sheet. I haven't done that, but this is the function I'll use. Just remember, it gives you everything to the right of any point that you plug in for C. So if you want to the left of that point, you just do 1 minus, and that will give you whatever to the left. Okay? Mass functions. A population or process distribution for a discrete variable x is specified by blah, blah, blah. This one. So mass functions are for discrete variables. So let's say you have some function. Okay, let's make it bell-shaped. Okay, I have some function. What it's saying basically is that for discrete variables, they're not as smooth, because remember, discrete is 0, 1, 2, 3, 4, blah, blah, blah. You never have any values in between. So your values only exist at solid numbers, okay, or natural numbers. So when you want to get the probability of a function like this, your function doesn't actually look like this for a discrete. You'll have, this is like, I guess, fancy way of showing it, but let's say this is 0, 1, 2, 3, 4. And let's say we're calculating the amount of people at position 1. Let's say we have 10 people at position 1, so you'll have like 10 variables here, and then you'll have some 10 variables or 20 variables here. I don't know. You get the point. You'll have like they're only at solid numbers. Nothing exists in between because they're discrete values. So if I tell you I want the probability of being between 0 and 2, then you're not going to need to integrate over the whole thing because, well, there's nothing in between. So what you'll do is you'll just get the probability at 1 and then add it to the probability at 2. And that's basically what this says. Now still, just like any distribution, your total should be 1. And so where the summation is all over possible x values, other interesting proportions can be obtained by adding various p of x. P of x, remember, p represents probability. So it's just like integrating, but for this one you don't integrate. So that's why they say p of x. In a particular, if a and b are integers with a less than b, then proportion of x. This is basically what I was saying, is that you just add them up. So if I had, usually actually what they'll give you is they'll give you some x values, and they'll give you some p at x values, and they'll give you like 0.2 at 1, at 2 is like 0.5, at 4, 0.3. So we've got 5, 6, 7, 8, 9, 10. So right now you see this adds up to 1. If I add anything, it becomes not a distribution because it's supposed to add up to 1. The probability always adds up to 1. You can't have 120%, right? And so if I want to tell you, well, what is my probability of being 1? Well, that's 20%. And so if I tell you, oh, what's my probability of being between 1 and 2? That would be 0.2 and 0.5. But remember, if you have your regular distribution, whatever it is, and I tell you this is not discrete, this is just a normal distribution, and I tell you I want the area under the curve between these two values, a and b, it doesn't matter if you include a or b, like between, let's say, a, this is going to be x, b. It doesn't matter whether it's inclusive or not, like for a normal distribution. It doesn't matter because it's like when you integrate, you're getting everything in between. And if you include it, like the integral is everything in between. Like it doesn't matter if you make it inclusive or not, right? Like when I integrate, it's b to a. You don't even get to decide whether it's included or not. And even in the syntax, when you write it, now when you read the question and it's clearly specifying it's included, do write it because you might deduct marks if you don't put it. But math-wise, you'll get the same answer because the integral doesn't matter. The integral doesn't tell you something is included or not. However, for discrete variables, if I tell you I want the probability between 2 and 3 is non-inclusive, then why would you add 3 to it? So it does matter because adding 3 will obviously change it because you're not getting any values between like the curve, right? Like you're not getting values under the curve between these 2 points. You're adding them up individually. So if you add up 3, it'll make a big difference. And so that's for discrete. you want to pay attention that if it's inclusive or not, it does make a difference. Because you see, here it says B inclusive, therefore they added B. But if B wasn't inclusive, you wouldn't add it. You would go all the way up to B, but not include B. Okay? So that's really, it's for discrete. For discrete variables, you just sum them up. A continuous variable x is said to have a normal distribution with a parameter mu and sigma. So mu is your mean, and your sigma is your standard, what is it called? Standard deviation? Standard deviation. Maybe it's not standard, but I know it's the deviation. I can't remember exactly what the wording is, but it is the deviation. And what it means is that when you have your graph, okay, what these two things tell you, your mu is the value of where, if you take the graph and you mirror it, it's symmetric. So if I go right at 2 and I mirror this to the other side, it will look exactly the same. That's what mu says. It's the mean value where the graph becomes symmetric. Because remember, if I put it here, the graph is not symmetric anymore. Okay, so that's the mean. Now, if you have values for the mean, like if they give you, 1, 2, 3, 4, 5, and they want the mean, you would add all them up and you would divide it by the number. So here, what you'll do is 1 plus 2 plus 3 plus 4 plus 5 divided by 5. That's how you'd find the mean. Now, if we want to go fancy, I believe, I don't want to scare you guys, but this would be from I at 0 to n of x at I. So basically we're saying the sum of x divided all by n, which is how many x's there are. Okay, so that is the syntax for it if you want to look fancy, but the mean is just you add everything up, all your values, and you divide it by the number of values you have. Now, what is sigma? Sigma is basically they tell you how do the values deviate from the mean. So remember, this is the mean. Your deviation variable, sigma, the bigger it gets, the more spread out your values are. Okay, so like for example, this is more spread out. If I have something like this is a lower sigma because you're not deviating by much. And so that's basically what your sigma and mu represent, is how compact, basically your sigma says like how compact is your data, and your mu basically tells you the value where your graph is symmetric. Okay, now we do have this big ass function. However, we're not using this big ass function, so don't let it scare you. We're gonna get into how you can get the same result without going all fancy with this function. Okay, so this is where we go into standard normal distribution. The normal distribution with parameters values mu equals 0 and sigma equals 1 is called a standard normal distribution. I'm just reading off the screen. You could do the same thing. So I'm going to stop reading it. But what you need to know is once it becomes a standard normal distribution, remember, not normal distribution, standard normal distribution, you use the value z instead of x. Okay? Now, what does it mean to be a standard normal distribution? Basically, somewhere at some time, some dude said, you know what? There is a certain way a bell curve looks that is just the standard bell curve, where now the mean is always at 0, which is where the graph becomes symmetric, and the numbers deviate at a constant rate of 1, which is your sigma. When your sigma is not 1, that means you're not standard anymore. And that means your variable's all over the fucking place. That's why it doesn't look like the standard bell, right? And so what we do is we have this table that gives you all the numbers for, this is given, that gives you all the numbers for your probabilities under the curve. So you don't have to calculate it using this big ass fancy function. Now, obviously you're like, oh, well, that's great. Then I'll just use this. But how am I going to use it? I'm so done with like having to scroll so slow. Where's my bar? There you go. You're like, I don't want to use this function. I just want to use this book for everything. But not everything is standard. Therefore, I have a solution. Standard normal distribution. You can obtain it from any normal distribution. So, if I give you a normal distribution with sigma does not equal 1 and your mu does not equal 0, then you can standardize it. So you can use the book. How do you do it? Let's say I have some function, I tell you, or I don't even give you a function, and I tell you this is your mu, let's say like it's 2.0, and then I'll tell you your sigma is, I don't know, what do we got? 3.6. And I tell you, well, find me a probability of x less than or equal to 3. Okay? Now, I don't give you a function. You're like, well, you didn't give me a function to integrate with, so I can get the area under the curve. So I can't do that. But I have these values that tell me the area under the curve for a standard normal distribution. So what I can do is I can take this x value, submit it in here, okay? So you'll have 3 minus your mu, which is, I probably chose wrong values, but don't worry about it. The way you do it is the same. Over sigma, which is 3.6, and you'll get some value, which is 1 over 3.6, whatever that is. Now, your z became the x. We just standardized the normal distribution that I gave you. So now this question turns into P of Z now, because now we have this value, which replaces this. We basically took the 3 and we were like, if this function was standardized, instead of it being at location, so remember, let's say this is like a very tight bell, and I'm looking for 3, right? Now, the standard normal distribution looks something like this. It looks all fancy and very symmetric. And you're like, well, how do I convert this 3 to, like, what is the equivalence of 3 on the standard normal distribution? That's where you use this, and it will give you the equivalence. In our case, it's somewhere on, 1 over 3.6. And you're like, well, if that's the equivalence, now I can actually use this page right here and get my values without having to do all fancy math. And so we will go to this page, and you see you have your z values. Now our z value looks ugly as shit, so we're not going to find it here. But usually you'll find it in here, and you can match it. So you see this will give you like 3.8, let's say, or this is negative 3.8, and then you'll go, if you want 3.83, you'll go to right here, and this is your percentage, which is 0.0001, or in other words, I believe this is 0.0001%. I'm not sure, but you get the idea. Okay, so that's the whole point of standard normal distribution, is that if I don't give you a function that you can integrate and get the area under the curve for your probability, then you'll just standardize it. As long as you have your mu, sigma, and x, you can standardize it and get its equivalent value on the normal standard distribution, the standard normal distribution. And then you'll be able to use the table. Okay? One thing to keep in mind is that, remember, for our exponential, it gives you to the right. So whatever you plug here for your value, it will give you to the right of that. However, your standard normal distribution will give you to the left of it. So whatever z value you plug in, it will give you to the left. So in this question, we wanted x less than 3, and we found this. So when you find a value here, that's going to be your value. However, if I said I want x more than or equal to 3, then I want whatever 3 is, I want to the right of it. How do you get that? Now, we do know the normal, or any distribution, the area under the curve always equals 1. So we know this whole thing equals 1. So now if I have to the left of 3, if I do use the table, here, let's remove all this. If I do use the table, let's assume this is the 3 equivalence. And let's say, obviously, I use the table and I get to the left. But I'm looking the one to the right. That's what I want. So I can take 1. I minus whatever, remember, this whole thing is 1. If I take that whole thing and I minus whatever is on the left, it will give me everything to the right. And so that's what you'll do. Just keep that in mind. Just, this will give you to the left and the exponential will give you to the right. All right. Now we are going to see how you can use a standard normal distribution for discrete variables. Okay, so it says the normal distribution is often used as an approximation to the distribution values in discrete populations. For example, blah, blah, blah. You could read this. The whole point, there's only one trick to discrete. It's literally the exact same way, except there is one. Oh, that's what it's called, standard deviation. So I guess I was right. Was I? Standard deviation. Oh, look at me go. Let's go. Okay. So the standard deviation is 35 bags. So this is your sigma. The number of bags lost by a small airline per week is approximately normal distribution of with a mean. So this is your mean value. And it's telling you what is the probability that they will lose at most for 20 bags. So at most, what they're telling you is that your x will go less than or equals to 420. Because what it says at most is I want, like, let's say this is your bell-shaped, and this is our 420. I'm telling you, what is the chances? The most I will lose is 120. So I want the whole thing until 120. When I say at least, it means you start at 420 and you go forward. Okay? So be careful with the wording. She did point it out a lot in the lecture, so you should be good with it. Unless you didn't attend, which is okay. I don't like attending either. But the trick with using a standard normal distribution with this one is you have to always add 0.5 to your number. So this will be 420.5. Now you might think, why is that? The thing is, I like to explain why it is because you will not remember if you don't. You will not remember it if you don't understand it. So remember, discrete values are solid numbers: 0, 1, 2, 3, 4, and so on. Let's actually use this one. 419, 420, 421. Now, if you use this, so remember, we have our sigma, we have all that. If we standardize it, because remember, for a discrete, if you want to get the distribution, you want to do P at A plus P at A plus 1, so on until you're, right? We don't have that. They didn't give us any of that. So as soon as you realize you can't do it, then it's standard normal distribution. So what do? We have everything we need, which is we have the mean, we have the sigma, and we have our x value. So z equals x minus, what was it, mu over sigma, I think? Yep. So now you just plug your numbers in. Let's say 420 minus our mu, which is 427 all over 35. Now this will work. The only problem is that from 420, remember at most is 420 included. From 420 to 421, what happens to the data here? This will affect, because remember in the standard normal, in discrete, this area doesn't have shit, right? Because discrete are solid numbers. But since we're standardizing it, we're saying that, oh, it's a smooth curve. So this area matters. However, when you just do 420, this will give you all the way up until here to the left. So the chances of you being 420 is not even there. And since we standardize it, it's smooth. So we gotta include the numbers here. And that's what we do. 420.5. Everything less than 0.5 goes with the 420, and everything more than 420.5 goes to the 421. Because remember, it's discrete, so technically there isn't things here. But because you standardize it, you're saying, oh, it's a smooth curve. So you gotta make sure that whatever is at the 0.5 more goes with that value. Well, everything 4.5 or less will go to the left, and everything I don't know why I'm saying 4. Everything like 0.51 will go to the right value. But obviously, basically what you're saying is if you're trying to look for 420 plus, what you'll do is you'll actually do 420.5 because you want to get this area as well, right? So you'll go from 420.5 onwards. And same thing if you're trying to get 420, you'll do 420.5 because you want to go to the left. I hope that kind of makes sense. Just remember, if you have a number line of 420 and I tell you, get me the probability, you want to add 0.5 to it. If assuming you want to go to the left. If you want to go to the right, of 420, then what you'll do is minus 0.5. So this will be actually 419.5. Okay, so just keep that in mind. I've had gum in my mouth this whole time, and you know, once you get like to the lifetime of the gum and it starts being chewable, it stops being chewable. That's where I'm at. So I'm gonna go. The lecture's over. Okay, guys. This is everything you need to know for week 2, and that's about it. Goodbye. See you guys on week 3.